David.
So I visited TAC. Thank you very much. It was amazing. And I also visited a number of other data centers in the US. And one in particular struck me, which was consuming around 36 megawatts, generating free AI slop meme videos. And,
yes. What we spent on cat videos is surprising.
Yeah, when someone figures out that it's not commercially sustainable, I mean, is that the kind of system that could ever end up in the hands of a scientific computing community? Like, I mean, what are people going to do with that kind of infrastructure when it's overbuilt?
So there's a lot of complications. Right? Short hardware lives are going to make that sort of difficult, right? Because if the bubble doesn't burst for 2 or 3 more years, some of that stuff's going to be ancient, and we may not want it, right? But and also just the way public financing works, it's going to be, it would be really hard. And, I've submitted now more than 12,000 pages of documentation to keep the leadership facility going and justify the budgets. If I ever said, we're going to wait out the bubble and buy it for 10 cents of the dollar in bankruptcy auctions, never would have gotten through the reviews, right? So to get this far. So it's going to be hard to acquire in that model. But I do think, yes, there is the potential for doing that when they're sort of desperate for things to run on them that will pay anything at some point. And by the way, I do think there's going to be a very viable and huge market for AI services because we can do incredible things. But, again, I should $1 billion a day just to pay for the infrastructure. The baseline projection is that right now, break even with people and costs and run costs and marketing is $1 trillion a year. In AI revenue. It would have to be a very big industry, right? So if they're very successful and they make $500 billion a year, half the companies are screwed, right? I think, there are some huge bankruptcies coming. We just don't know who, right? So, if they get to $1 trillion in 5 years, that's too late. There'll be $5 trillion in the hole. So they need $1 trillion next year, and they're not going to get it, right? They might get $200 billion. I'm not saying AI is going to go bust. I'm just saying we put a lot too much fiber in the ground in the dot-com boom, and there was a huge bust, but it turned out the internet was still important, and computers did in fact change the world. But we burst these bubbles before. But yes, I do think that will be there, and exploiting perhaps systems built. Right now there's a lot of cryptocurrency rigs sitting around sort of doing nothing because everybody's replacing it with AI hardware. If we can figure out how to exploit this stuff, there's a lot of opportunity there.
Andrew.
Yeah, Dan, great breakdown there. I couldn't quite do the math real time, but can you share commercial electric rates?
I was figuring 7 cents a kilowatt hour.
7 cents kilowatt hour?
Yeah,
okay.
6 or 7 cents a kilowatt hour, with demand charge and stuff like that. So,
okay, yeah.
That's what you pay?
Yeah. So, which is, like way lower than Germany is paying right now, but more than Finland. You can arbitrage around the world. China's been trying to do some big incentives around power costs, but...
and Elon is sending everything to Mars.
What's that? Yes, yeah. Data centers in space, also known as Twitter ran out of money, so he merged it with XAI. Then XAI ran out of money, so he's merging it with SpaceX. But no, it's about data centers in space, because what this problem needs with your 6,000-pound racks is a $50,000 per kilogram launch cost to put those racks in orbit, right? So, yeah, and also cooling works great, up there, right? And if you thought Los Alamos had bit correction problems from solar radiation at 8,000 feet, go up a little higher and try that, So we'll lead shield it because that's cheap to launch too, right? So,
marginal comment. Have you thought about stand-up comedy?
Are you sure that's not what I do now? Yeah.
I'm just highlighting.
Yeah.
Andrew,
students
you
listen
were...
to my lectures?
Oh, you finished. Cool. Amal.
Thank you for the great talk. It was really amazing.
It's the last afternoon. I got to keep everybody awake.
Yeah, we were awake. So I have a question. You say that we have to put on more efforts to make this AI use effectively the architectures. So optimizing AI mainly. And I think that what I like calling HPC wisdom is already there. We, as HPC people, we already know how to use perfectly, or almost perfectly, the hardware for our simulations. So who do you think is gonna do that? Is it our responsibility as HPC people go to the AI people and teach them how to use the hardware correctly? Is it for the facilities to hire people to help AI developers optimize their software? Is it for the vendors? Who is going to do that?
Yeah, I think the HPC community has a huge amount to bring to this, right? And so I don't know if it's our responsibility, but it's certainly our opportunity, right? Is to have them, and you've watched so many of the wheels get reinvented, right? Mixture of experts is, what if we built a cluster of these things, right? Which was the 90s again in HPC, right? The creating shared memory out of NVLink is all the shared memory lessons of the late 90s and superdomes and stuff like that. I mean, we already know how that story ends, right? Nickel is MPI for NVLink because they've invented, they think broadcast and reduce, it turns out, are really exciting network operations that nobody's ever thought about before. But yeah, when's the last time you saw an AI tutorial that was about debugging and optimizing your code or cache block tuning for AI models, right? This is something we worried about because traditionally in HPC, we're dirt poor by comparison to enterprise IT until, it's a fairly recent phenomena for us in the AI space that if you tell them, if you want to accelerate this, you're going to have to spend another $1 billion. And they just go, okay, what would we do with $10 billion, right? So, it was, we're going to figure out how to build this machine at $10 million and do $100 million worth of work on it, right? So yeah, I think we have an incredible amount of effort and skill set, right? Stuff like the hearing about from Japan this morning, right? Actually teaching optimization. I actually taught a course of let's have the AI generate your code, but now let's talk about optimizing your code, and maybe you can use AI to do some of that. So I taught a grad course in the fall in computational methods in the Odin Institute, and for those CSIM students Karen was talking about. So the cheating was they had pretty bad instructors, but they had really good students in that program. And the final project was essentially take a code from your lab and make it go faster, right? And although we hear about how hard optimization is, the average result of one grad student 1 month was like 35% on research codes. Some, did surrogate models and got like 3,000, but the one or two didn't get anything out of it, but almost all of them could do it. But one student had the AI write the code for a problem he was interested in. He's like, well, I couldn't understand it, and it didn't seem fast or efficient. So I tossed that code and just wrote the big code myself, and then ran it through a profiler, because we'd showed them to run through profilers. Who's the last person to run a profiler on a PyTorch model? Good for you. I knew I liked you. And they said, then they asked the AI to say, use cache blocking and 2 or 3 other things on this part of the code that was identified in the hotspot. And so they had the AI just rewrite the part of the code instead of the whole code, and their end result was much faster than just asking the AI to build the whole code and optimize, right? So I mean, I also think, if you're not using AI code generation tools, you're being silly, right? They're awesome, and they do amazing things, and they're getting so much better so fast right now. So you should use them, but it helps to know something about how to figure out if something is performant or not, or performs the way it should, and how to make it better. And so I think these are skills that our community has that could be hugely valuable to the rest of the community, again, when they start thinking about how much stuff costs.
Shane.
Perfect. So we're having to spend a lot of money on a lot of memory.
Yeah.
And I don't know about you, but the sort of scientific workloads we run don't use a lot of memory. And I don't really see, one of the example programs that came up in one of the talks earlier is a thing called GROMACS, which gets used a lot. That uses absolutely bugger all memory, really. Mm-hmm. It runs well on a GPU, but you're buying these huge memory GPUs.
Runs okay on a GPU.
Yeah, well,
that's faster than a CPU. But
yeah, but that's the other thing as well. That's the
now
other
that
thing
CPUs cost a 20th of what a GPU costs, you have to rethink some of that. But yeah.
Yeah, so. Yeah. I don't know about a lot of other people here, but I started out in 8-bit computers, and I went right the way through MIMD, through SIMD vector processors, into clusters, and now into GPUs and AI and all that other bullshit.
We are old. Yes.
Old, I know. But the point is that to get the most out of any of these machines, it was always about understanding the underlying architecture. And I think one of the problems that we do see a lot, particularly with modern programmers, is an over-reliance on compilers and the compiler optimizations and not actually looking at what the hardware is doing and looking at, I mean, I remember sitting with a
I think
mass
you might
part.
be exaggerating, thinking that most AI developers know what a compiler is.
Well, yeah. But I mean, I remember sitting with a book of opcodes and latencies for the mass pass supercomputer I was working on, and actually figuring out just what instruction order would go best and get me the same answer, but save me a few clock cycles on something that was going to go round and round a billion times. And so I do feel
but
like...
did you think you could have just spent $1 billion more and gotten your problem solved instead of doing that?
Well, we didn't have the money. That's the problem.
Right,
So we're kind of being forced into buying these machines because that's what the market wants to sell, because they want to sell to a particular market. And this is not a very good question, I'm sorry, but this is...
No, I get the gist of it, right? And it's true. I mean, I will say one reason we're having to buy so much memory is because the von Neumann bottleneck still works and memory bandwidth is a thing. And the only way you get memory bandwidth is by putting DIMMs in every single channel, right? And that means now you have to buy 32 DIMMs, to have a server, an AMD server filled up, right? And DIMMs are now $350 a piece. So you're $10,000 in the memory system before you buy a chip, right? So, and whether you need the capacity or not, you definitely need the bandwidth, right? So we actually, our Sapphire Rapids nodes, we run HBM only. And there were two reasons. One is, I have Ice Lake and other nodes if you need the capacity. But two, the only way I could guarantee the users wouldn't use the wrong memory is just not install it. So I'm sure they're running out of HBM because nothing else is there. And that removes one optimization space that I have to deal with.
If I can actually
again, that is the sort of my big point about like the way the NVL72 nodes are configured is it's around our perception of one really large problem and how it performs, and not how most problems actually perform, and nobody's doing really the analysis. There might come a time where the vendors aren't making 80% of their money selling one kind of rack to hyperscalers, and we can get back to saying, sell us what we actually need.
So, Nathan.
Dan, so I had a couple of thoughts, but I'll just comment one of them. Do you have any idea why perhaps these, I mean, you clearly articulated that we're buying hardware we don't need, the vendors know we don't need it, that are way too sophisticated for
I'm
the
not sure they
average,
know. They just
the average
don't really
user.
care.
I think they know, especially when they talk about the needing hundreds of these nodes to start to get performance and stuff.
Well,
but so they're designed for a different market, perhaps the giant LLMs, which a small number of people are training on. So do you have any thoughts on why a market hasn't developed at the low end? Like, it seems like an obvious market force should have developed to fill that end.
Yeah, I think it's just all happened too fast. I think it will develop, right, over the next couple of years. But, the notion of, if you remember like 2017, 2018, right, or like 2006 to 2018, when we talked to cloud vendors, right, it's like, why do you HPC people waste all this money on the network, right? I remember distinctly with like the Microsofts of the world, Ethernet's fine, you don't need these advanced networks, you're spending way too much money in HPC on those. And then AI came along, in 2022, I think Microsoft bought 22,000 miles of InfiniBand, right? We have 100 miles, and we used to be one of the biggest customers, right? So, and now they're like, why would you run with only the high-performance networks you have? We have way more. It's not like these are well thought out. They're reactionary to these huge forces in the market and huge spending. So I do think, I'm starting to see a lot of faculty coming and saying, what if we didn't buy Blackwell's or the GB class machines and I want RTX GPUs, I'm gonna make my code fit on them because they're sort of semi-affordable and air-cooled, but have slower, crappier RAM and 1/64th the 64-bit performance of but they're like, I'm willing to live with these limitations to get, one in a box I can get in less than 6 months. So I think that market will emerge, and I think we'll see it. NVIDIA used to sell a lot more SKUs, right? The L40s and things like that, right? I think they'll come back. I just think right now there's a limited number of wafers in the world, and you might as well make the most money off each wafer you can get out of TSMC, and that's building the big chips and selling them at a premium price. But we need demand to sort of get aligned with supply for people to start specializing in these things. Because, I mean, I don't blame either the SSD or the chip guys for making the most out of each wafer that they can. But at some point, we might be able to make more wafers than we can sell at $60,000 a chip, and that stuff will happen again.
Jason.
Hi. So I made a lot of notes that I'd be asking you with a shit-eating grin, but I'll skip all that. Would you expect more DRAM fabs as a result of the massive prices, or do you think
I don't know.
First?
First order, yes, right? I think there's a rush to build new fabs. Part of it is the sort of sovereign supply chain thing, right? All the fabs being 90 miles off mainland China. Some people are starting to think that might have been a bad idea. So there's a huge push in the U.S. to build fabs that are clearly not going to be economically competitive, but we're just going to build a lot of them anyway, right? I'm not sure they'll be the very latest node fabs forever because they're just so expensive. But the other thing is, the guys building the wafers are also pretty smart, right, and respond to the market. And they've been burned so many times by the spike in price and then the crash in price. And that's why I distinguished hard drives from flash drives, right? Because hard drives are mechanical. You can hire more people, run more shifts, set up another production line. You don't buy a $700 million machine from ASML to start the lithography for your next line, right? And fabs are, fabs are so expensive with multi-billion-dollar startup costs, right? That you're running them 24 hours a day anyway, right? There's no capacity to add shifts, and you need new, EUV lithography machines to add lines that you just can't get. But so it's 4 or 5 years to bring the supply online. So I think the math that the Microns, Hynixes, and Samsungs of the world are doing is, we're making a fortune right now. You can sort of see how they're positioning to get out of each other's way. Samsung exiting some of the consumer SSD, Micron exiting consumer RAM, so that each of them can raise the prices independently. But they're saying, is this just a gold rush right now? And if I spend billions of dollars on a fab, it's going to come online in the end of 2028, and then the bubble will be burst. So I think they've been reticent to start throwing a bunch of money into scaling fabs as fast as they can, because the history of memory prices is a sine wave.
Yeah, right? You're sensing the same thing they are. That
maybe this is a bubble, and that maybe it'll last for 3 or 4 years, but we need 4 years to get a fab online, and are we going to feel stupid at the end of it? So I think to first order, yes, because I see fabs, but I think there is some caution in the industry because they've been burned so many times on this.
It seems that SK Hynix is the one that are leveraging it seems that it's ahead of Samsung and Micron. But the open question that I had once upon a time was, and Andrew remind me that, the guys, our friends, Bob and Samantika and all the ones who went from Intel to Samsung in the US for, a couple of years? And I went, Robert Wisniewski was keynote here. There are still photos of you sitting in front of a Samsung banner that I have in my garage in Walmart. Right? So that suddenly disappeared. And I made a couple of questions. Okay, why? What have I done wrong? What? I said, well, someone told me, look, this is how we manage, this is how people in Samsung manage stuff. Right? So there are certain benchmarks. You don't do that, out. There is Korean, I don't know what's the word, but there is a family type of business. There is a word for something like that. But I still have the doubt, do they know something that we don't? In the same way that Jensen bought Equihired, I don't know, grow for $20 billion. What is buy? So those are just reflections. It's not a question.
He didn't really buy Grok. He bought the people and some of the IP, but that was largely to manage how much memory they have to buy, because Grok, is this in-memory processing architecture to, put more SRAM in the GPU, reduce the amount of external RAM. Because NVIDIA spends a lot of money with Micron and those guys on the HBM to sit on those GPUs. But so I think that is a memory play. But I think with the Samsung thing, for instance, right? Again, this is the oil boom for them, right, or the gold rush, or however you want to put it. But they were investing in new technologies to sell more differentiated products, and then we got into a market space, 23, 24, 25, where for every wafer they can put out of the factory, if they just make DIMMs, they can increase their margin on it by 50% per wafer. with no R&D and no innovation, right? So if you can wildly increase your margin on every single thing you can build to an arbitrary level, and I've heard anecdotally about certain large cloud operators sending out purchase orders to storage vendors for SSDs where the price is blank, and it's like, when you can get us this many, just fill in the number and we'll pay for it, right? It's really fun to negotiate discounts in that climate, but when the price you're competing against is infinite. If they can take every wafer they can build and sell it at any margin they want, why would they invest in anything new?
Correct.
So that may be why some of those far-flung R&D efforts aren't happening there, like the stuff Bob was doing.
I will give the word to Jeff, but before that, I want to ask Simon a question about what Europe is doing. I know that you are not European, but what's happening with, I don't know, the hardware designs, the Europe for HPC, all these initiatives in Europe, but Jeff has been waiting to say us.
So I keep coming back to your two big questions here about, can we take advantage of these different things? And if we go back more than 30 years, we could pay for designing true supercomputers, big vector machines. But since that time, if you look at Spark or IBM or MIPS, so, we've been taking what we could get, which is business-based chips or GPUs, or not GPUs, but toys to teraflops, gaming chips, putting them together, strapping all this stuff together, x86, and building whatever we could in the supercomputer world. So in some sense, we as an industry have been answering that question for decades. However, then when I think about this a little more, so I think just the pace of change here is happening, and the scale of it is so different. In some ways, it's a different question than we've been fighting against, or working with through the decades, it seems. So that's more of a comment, I guess, than a question.
Yeah, it's an extreme scale, but there was that extreme point in the late '80s, early '90s, right, where the end of the Cold War was drove 2/3 of the companies that were building supercomputers went out of business in about a 3-year span, right? Connection machines, Sequence. There were a whole bunch, right? And Cray morphed 6 times since then. But BB and Butterfly, you can think of all the machines that were out there then. And the driver was the Cold War ended, and the US stopped pouring infinite money into code cracking machines that were custom architecture. And the commodity computing market was exploding so fast at the end of the 80s, and this was sort of the core insight of the Beowulf project, right, to commodity clustering, was microprocessors are it. They're going to build microprocessors that look like these microprocessors, the Intel-based ones. We need to figure out how to build scientific computers that use those, because if we're going to rely on custom designed gallium arsenide large vector circuits, we're going to have no suppliers, right? And I feel like, and again, a lot of people didn't adapt. A lot of those companies died, right? That didn't adapt in time, because it was a pretty dramatic shift in the marketplace. And I think this is similar, right? And you hear people bemoaning, we're not going to have native FP64 performance improve in the future. And I think at this point, no point in whining about it. It's just true like that we were going to have to use microprocessors. So let's figure out how to emulate it. Let's figure out if we can do a little bit less performance. Let's figure out mixed precision algorithms. There's so many things we can do to mitigate that problem. And I think that's where our energies need to be going. This is where the market's going to go. We can't change that, right? It's just where it's going to go from, in scientific computing. We're just not big enough. So if this is what's there, let's start figuring out with tens of thousands of smart grad students who are younger and smarter than we are at this point, how we're going to adapt to this problem, because I think it can be done. Yeah.
So you could say that our industry isn't in a transition, we're in a rupture right now.
yeah, the gradient's higher, but it's happened before, I think, is the lesson there, right? So call it Beowulf 2, figuring this stuff out.
So, unless, Simon, you want to comment on what I floated here, or no, pass. So, I think that he deserves an applause.
Or booing.